Now I know it's working. Well, seeing my face is a necessary condition for it to be working, but it may not be sufficient. We'll see. So, lecture 3.3, this is a very short lecture. We're going to talk about the approximation of transient response characteristics. And we're going to talk especially about when that second order approximation for a higher order system holds true. That's like our most important concept to discuss in this lecture. So, certain higher order systems can be approximated as second order systems and can be characterized by the parameters in the preceding section. This includes systems with zeros. In the preceding section, we assumed the second order system had no zeros. So, in fact, in lecture 3.4, in a moment, we're going to do an example of a second order system with a zero in it and see what happens. Like, do our analytic predictions from the second order derivation from last lecture, do they hold when there's a zero in there? I don't want to give it away. I'll give you a reason to stick around, in addition to getting your test back at the end of class. Okay, so the conditions for these higher order systems, or even second order systems with zeros, to use the analytic derivations that we got in the last lecture, we, in order to use them with any confidence, we have to have the following conditions to apply. So, higher order poles are significantly leftward, so that's one condition. To expand on that, higher order poles have significantly more negative real parts than the dominant second order poles. So if we have a complex plane here, and our dominant second order poles are here, they're only dominant if they are the ones that dominate the behavior. If you have any more poles, we're saying, okay, you can have them, but they have to be significantly leftward of these. So they could be out here, that's fine. These two would still dominate, and we would be able to use that second order approximation for like settling time or rise time, like those nice expressions that we derived in the last lecture. Actually, we didn't derive them, we just wrote them down. I didn't derive them, except for maybe for the first order case. I think I derived that one. So it's fine if they're out here. These are okay. But if we have like one that's in here, we would say, nope, too close, too close. And so a good guideline for how close is too close is that they should be at least 5 times as negative. So if this is like -1, then this should be at least like -5, okay, in order for us to feel comfortable with the second order approximation. And if they're like, way out here, then we'd be more comfortable with that second order approximation. But if once they get in here, we would say, no, we're not comfortable with it. We might still use those expressions as a starting point for our design. That's fine. And really, we don't have a lot of other options, so we'll often still use the approximation. But we'll know that it's not very valid. Okay? So that's something to remember. These poles that are way out here, the reason we can ignore them is that they contribute a relatively small amount to the transient response. Remember that these poles are going to generate terms in the transient response, specifically the homogeneous response, right? That are going to have negative real part plus some imaginary part times time, right? And if that real part is significantly larger, this is going to be an exponential decay that happens really quickly in time, right? It goes away quickly. So the transient doesn't hang around long enough to contribute much. That's why we say these ones out here don't contribute very much, and we can ignore them. Okay. Another thing that we would need to have be true. So these are all, you could say, we're not being super logic driven. We would say and. Higher order closed loop poles and zeros nearly cancel. Well, I guess it kind of depends. This is why I left it ambiguous. It could be or too. So as long as we don't have, so they could be out here and they don't need to cancel. But if they're in here, if they're close, we would need a pole and a zero to cancel in order for us to use the approximation with confidence. So closed loop zeros near the closed loop second order pole pair are nearly canceled by the close proximity of higher order closed loop poles. So if you have a pole and a zero that are close, that would be okay. Even if they're close to these dominant ones, but they cancel each other approximately. Because remember, a pole's in the numerator and then a zero's in the, or a pole's in the denominator and a zero's in the numerator, right? So if they're like on top of each other, their effects approximately cancel. Okay, so that's fun. It's another possibility. And then the third possibility is that uncanceled closed loop zeros are distant from dominant poles. So say we have a closed loop zero that's out here, or we have like a complex conjugate zero pair that's back out here. These are fine. These are okay. But if they're close, they need to have a pole on top of them that cancels them. So what we want is this complex conjugate pair of poles to be kind of by themselves, not affected by other poles or zeros nearby. And if they are, they should be canceled or nearly canceled. But as I said, I mean, these things are nice guidelines to know when these approximations are true. Like, for instance, we drive the expression for a second order system that the settling time is equal to 4 divided by zeta omega n. This only technically holds exactly for a second order conjugate pair of poles that doesn't have a zero associated with it, and there are no other poles in it, in the system, right? So this is only true for a very specific system. Second order, no zeros, right? No zeros. There's no E in zeros, is there? I don't know. I can't remember right now. Do you guys know? Just like that? Okay, cool. I'm marking it correct. So, we're still going to use this, even if these approximations don't, even if these conditions aren't perfectly met. Maybe we have a pole that's kind of close. Maybe we have a zero that's kind of close. We'll still use this approximation for settling time because we don't have anywhere else to go. So we'll still kind of use it. And we'll know that it's not a very good assumption. And then later we're going to check. Okay? But it's a place to start. So let's, so unless there are any questions, I'm going to actually do the example and we're going to see something. So any questions on this? Okay, let's do an example.